Flipped classroom presentation for Further Maths Unit 5, confidence intervals 3 with small samples. Confidence limits for the mean of a normal distribution with unknown variance, and we're going to consider small samples. In the previous section, you looked at situations in which the sample was large enough so that the sample variance and unbiased estimate for the population variance could be used as a good approximation. For an unknown variance, the sample unbiased estimate of sigma squared is s squared, which is defined to be that expression, or we can rearrange and get that expression or that expression. Now I prefer the third expression, this one, but then it depends on the information you are given in the question. However, if the sample is small, the sample variance does not give a sufficiently good estimate for this method to be used. Then a different distribution, the t distribution, can be used to model the situation in such cases. So when we are using this t distribution, we need that the underlying distribution must be normal, and this is a reasonable assumption when the distribution arises from a natural population, and the sample must be random. And this is the graph of a t distribution with the probability density function above. The t distribution, like the standard normal distribution, is symmetrical about the origin, but not as pointy as the origin, and its tails are slightly higher than the normal graph. It can be shown that the t distribution gets closer to the standard normal distribution as n gets larger. So, using the t distribution, the method for finding a confidence interval is similar to that used with the normal distribution, except that instead of using z values obtained from normal distribution tables, you use the t values obtained from t distribution tables. And as well as depending on the confidence level chosen, the t value also depends on the number of degrees of freedom. The number of degrees of freedom is usually denoted by the Greek letter nu, and is one less than the sample size n minus 1. This is because for a given value of the mean, n minus 1 of the data items in the sample are free to take any reasonable value. But the value of the last one then is fixed, as is the last one left, and there's only one space. Then, to obtain a symmetrical 1 minus 2 alpha 100% confidence interval for mu, using the t distribution we have. So there's the t distribution graph, and I need a 1 minus 2 alpha times 100% probability within the two boundaries, giving us alpha on each end. So we have, so the probability of t less than minus t for the alpha, and t greater than t for the alpha, giving us, so the probability for the two ends is alpha. So putting those together, we get that we need 1 minus 2 alpha for the gap in the middle. And substituting t being the test statistic and rearranging, we get that the probability of x bar minus t of alpha times the square root of the variance, which would be s divided by square root of n, variance being s squared over n, so square root of that. And so mu is between x minus that expression and x bar plus that expression, must be 1 minus 2 alpha. Therefore, the confidence limit, so the end points, would be x bar for the sample plus or minus the t from the tables times the square root of the variance of the mean with our estimate of s squared. So let's look at an example. So the company manufactures electrical components which they state have an average lifespan of 500 hours. The inspector tests 15 of these components and finds their lifespan x hours. The results are summarized by, so the sum of all the x is 7,338, and the sum of each x squared is the second expression there. Find a 95% confidence interval for the mean lifetime mu hours of the components. So looking at the data we are given, n is 15, which is small. The sample mean is the sum of the lifetimes divided by 15, which gives us 489.2. Our unbiased estimate of the variance, s squared, is 1 over n minus 1, which is 14, times the sum of x squared minus the sum of x all squared over n, giving us 2036.457 and so on. Don't round up too early. So the sample size is 15, so nu is 14, so 95% gives us the end points being 5% split between 2, giving us 2.5%, so we're looking up 0.975 in table 7. So 0.975 for p, and nu being 14, we get the t value, the t alpha value, to be 2.145. Therefore, the confidence limits would be x bar plus or minus the t for alpha times by the square root of the variance of x bar, which is s squared over n. So we have 4.89.2 for x bar plus or minus 2.145 for the t times the square root of s squared over 15, giving us end points 464.21 and 514.2, so the interval is between those points. That is our 95% confidence interval. Example 2. A zoologist wanted to perform an experiment to find out how many trials a rat needed before it became familiar with a particular maze. He performed the experiment with 8 different rats. The number of trials needed by each rat was those values there. Find an approximate 90% confidence interval for the mean number of trials the rats needed before they became familiar with the maze. We assume that the number of trials is a random variable with a normal distribution. So this time we need to add up all the values to get the sigma x. So sigma x became 118, and squaring each value and adding them, and we get 1898. So we have 8 values. For n is 8, which is small. Our sample mean is 118 divided by 8, which becomes 14.75. And our estimate of the variance, our s squared, is 1 over n minus 1 times the sum of x squared minus the sum of x all squared over 8, giving us 22.5 as our estimate of the variance. So the sample size is 8, so our nu is 7, n minus 1. 90% gives 5% for each n, so alpha is 0.05, so we look up 0.95. So this time we're in this column and we go to 7, so we get our value for t to be 1.895. Therefore, the confidence limits would be the x bar plus or minus the t from the tables times the square root of the variance, s squared over n, giving us 14.75 plus or minus 1.895 times the square root of 22.5 over 8, which gives us the interval between 11.57 and 17.93. One last example. 10 people were asked how many hours on average they slept during a night. The 10 answers were those. Given that the mean number of hours of sleep is normally distributed, calculate 99% confidence limit for the mean number of hours of sleep during a night for the population. So we need to work out the sum of x and the sum of each x squared, giving us those values. N is 10, which is small. So our sample mean is x bar, which is 78 over the 10, giving us 7.8. Our estimate of the variance is 1/9 now times sigma x squared minus sigma x all squared over n, giving us a value of that. Don't round up too early. So we've got a small sample, so we need to look up table 7. 99%, so we need 99% in the middle. So we have 1% to split between the two alphas. So the alpha in question is going to be 0.005. So we are looking up 0.995 with nu being 9, and we get 3.250 for t for that value of alpha. So our confidence limit again, so we substitute in, so 7.8 for x bar plus or minus the t that we've got from table 7 times the square root of the variance, which is s squared over n, and we get limits, endpoints for the interval 6.74 and 8.86. So whenever you've got a small sample, it's got to be, and an unknown variance, it's got to be the t distribution. And that's the end of the presentation for small samples with confidence limits.